Hi everyone, welcome to the video answer key for the Ideal Gas Law Practice Worksheet. So for every type of problem, I'm going to do one example and you can use that as a guide for you to do the rest of the problem. So for number 1 through 7, they are just using the Ideal Gas Law, which is PV equal nRT. And you can already see that I've already done number 1 and 4. Now the two key things to keep in mind when you do these kind of problem is that how do you recognize that you need to use PV equal nRT? And the way you do that is that they have already given you 3 out of the 5 variables present in your equation. So for example, I am going to take number 6 and I'm going to first start by identifying what's given to me. And first I was given mole, and then I'm seeing that I'm given P, and then I'm given T as well. Now you know that you have to use PV equal nRT because that's already 3 out of the 5 variables present there. So you have P, you have N, and you have T. And R is always known. And that's the second thing actually you need to keep in mind is that make sure to choose the correct R value. You choose the wrong R value, your answer will be incorrect. So then I'm just going to keep going and using PV-nRT to solve this problem. And they are asking me for volume. So then I'm going to rearrange this equation so that I have volume on one side and everything else on the other side. So that would give me nRT over P. Now just a matter of plugging in the correct number. In this case, that's mole. And so for R, you want to choose the value that has millimeter mercury in it. But if you look at the list that I've given you, there is no millimeter mercury. However, it is torr, and you know that 1 millimeter mercury is equal to 1 torr. So I'm going to basically convert this to torr. And then I'm going to use the R value that corresponds to that, which is 62.36367 L torr mole Kelvin. And then multiply it by 18.4 plus 273 because we got to convert that to Kelvin. All over P, which is 47 torr. And when you punch that into the calculator carefully so you get the right answer, you will get 1.28 times 10 to the third liter. Let's go ahead and go over a problem where you have to calculate the density of a gas. So I'm going to take a look at number 9 where it asks you to determine the density of oxygen gas at this pressure and temperature, assuming that the oxygen gas is ideal. Now, this is kind of a giveaway that you need to use the ideal gas law somewhere in there. So PV equal nRT. Keeping in mind that density, the unit of density is gram per liter. Step number 1 in approaching this question is that I want to first look for a number or a value that could correspond to gram, because that's what I want in my density. Now I'm looking at, I have pressure and temperature, but they don't give me anything in gram. But I do know there's one number that you can get from the periodic table that contains gram, and that is the molar mass. So I'm going to start by calculating the molar mass of O2. As a reminder, O2 is a oxygen gas. It is a diatomic gas. So the chemical formula is O2, and because of that, the chemical or the molar mass is 2 times 16, giving me 32 gram as the molar mass for O2. Now, second step is that since there's no information given to you about the number of moles of gas present, you are going to assume that there is 1 mole of O2 present. So I'm going to say assume 1 mole of O2 present. Knowing now that I have 1 mole of O2, I can actually use PV equal nRT in order to figure out the volume of O2. Now that volume is going to be in liter, right, the unit, and that's exactly what I want here in a density. So I'm going to just rearrange the equation over P, and then I'm just going to plug in all my values. So after inputting this into the calculator, I should get 34,117. So liter of O2. After you have gotten the molar mass and the volume of O2, you want to now determine the density. So that's our step 3. So calculate the density. And reminder that the formula for density is mass over volume. And mass we have found here to be 32 gram, and that's per mole. So 32 gram over, I have just found my volume. So that's this number. So I'm going to write that as 34,117 liter. And that would give me, so the density of oxygen, or O2, would be 9.38 times 10 to the negative 4 gram per mole. Next, let's do a stoichiometry problem using the ideal gas law. So number 10 and number 11 is type number 1 in your notes, which is where you were given the pressure and temperature of chemical A. So in this case, it's CO2. And you were given the mass of chemical B, which in this case is copper carbonate. And you are asked to calculate the volume of chemical A, which is CO2. So the key to recognizing that a problem is a gas stoichiometry problem is when you are given information that not all of them belong to one chemical. So in this case, we have volume, pressure, and temperature belonging to CO2. Now actually volume is not even given to us, but pressure and temperature belonging to CO2. But mass is belonging to copper carbonate. But the good thing is that we can go from copper carbonate to CO2 or vice versa using stoichiometry, because there is a mole ratio between these two chemicals. And it's exactly what we're going to do. So first up, step number 1 is for you to do stoichiometry. So step number 1, I want to use stoichiometry to go from gram of copper carbonate, because that's what's given to me, to moles of carbon dioxide. Now I want to go to moles of carbon dioxide because then I can use this moles number to plug into PV equal nRT in order to find V of CO2. Alright, let's go ahead and start with my given, which is 182 gram of copper carbonate. I want to convert that to moles of copper carbonate by using the molar mass. And I know that the molar mass is 123.55 gram of copper carbonate. Then I'm going to use the mole ratio between copper carbonate and CO2. I know I want mole of CO2 at the top and mole of copper carbonate at the bottom. And they have a 1-to-1 ratio. So what I should end up with is 1.473 moles of CO2. Now as I've found moles of CO2, I can use mole of CO2, that what we just found, to plug in to PV equal nRT to solve for V of CO2. Now I'm going to rearrange PV and RT to isolate V to solve for V. So that actually gives me this. And then now it's just a matter of plugging in the equation. When you punch all that into the calculator, you should get 17.2 liter of CO2. So that's type number 1. Type number 2 is number 12 and number 13. So here is how you would do number 12. You can pause the video now to check your work to see whether you did that correctly. I want to go over now number 13. So number 13 is type number 2 in our list of 3 types of different gas stoichiometry problem. And this is where you were given pretty much all the information belonging to one chemical, but you are asked another piece of information about a different chemical. So number 13, they asking you for the mass of sulfuric acid, so H2SO4. But they are giving you 15 liter of SO3 gas, so that's V of SO3 in a chamber at 1 atm. That's pressure of SO3, and 25 degrees Celsius, which is also the temperature of SO3. Now, first thing you want to do is that I'm recognizing that they have given me the volume, the pressure, and the temperature already belonging to one chemical. And I know that my ideal gas law, PV equal nRT, those that was given to me, P, V, and T, that's already 3 variables in this one equation that's already given. And then R, you know that you always know, you just got to choose the correct one. So when they are given to you this abundance information and they all belong within one equation like this, it's basically a hint that you should probably use that equation right away and then figure out the only missing variable in our equation. In this case, it's N. And N in this problem in particular is N of SO3. So I'm going to first do PV-nRT to solve for N of SO3. So I'm just going to rearrange the equation. So that'll be N over PV over RT. And you just plug in a number. After punching your calculator correctly, you should get 0.6133 mole of SO3. Now so now you have mole of SO3, but you want mass of sulfuric acid. Now there's a mole ratio between SO3 and sulfuric acid, and that's a 1-to-1 in my chemical formula reaction. So I'm going to use stoichiometry, and I'm going to go from mole of SO3. I'm going to go from mole SO3 to gram of H2SO4. And the way I do that is that I'm going to take the number we just found, so 0.6133 mole of SO3. I'm going to use the mole ratio between these two, which is 1-to-1. And then I'm going to convert mole H2SO4 to gram of H2SO4. Punching this into the calculator, she gives me 60.16 gram of sulfuric acid. Now I think in the answer key it says 60.17. That's okay. It's just a difference in molar mass giving you a different final answer, but it's not a big deal. Alright, notice that the difference between number 10, 11, and 12 and 13 is that in 10, 11, you do stoichiometry first, and then you use PV-nRT second. And in 12 and 13, you use PV-nRT first, and then you use your stoichiometry. So just keep in mind those are the differences between these types. Now lastly, the last 2 questions on this worksheet is regarding basically type number 3 in our 3 types of gas stoichiometry problem. And this just happens to be the easiest one because it doesn't require as much calculation. Now let's take a look at what exactly is given to us. So it's asking for the volume of gaseous methanol, which is CH3OH. So that's what it's asking. They're asking us. And it's given us at this particular pressure and temperature by the complete reaction of this much volume. So I'm going to use a different color now because that's the number for a different chemical. So carbon dioxide, V of CO2. So now the conceptual part of this, or a key concept that you need to understand, is that we know that 1 mole of any gas will take up 22.4 liter. So whether it be CO2, H2, or methanol, or water gas, or water vapor, 1 mole of each of any of those would occupy 22.4 liter. So what this means is that regardless of its identity, this holds true. So regardless of the identity of a gas, that holds true. And so you can actually use a bit of a shortcut to approach this problem. So you can actually disregard this pressure and this temperature. Before we get started, I want to see whether my equation is balanced or not, and it's already telling the problem it's unbalanced. So I'm going to go ahead and balance it. I think that all it needs is a 3 in from H2. So then I can go from V of CO2 to V of methanol just by using the mole ratio. So the mole ratio in this case is just simply a 1-to-1. So I'm going to start with 17.9 liter of CO2, and I'm going to multiply that by 1 mole of CO2 to 1 mole of methanol. And that will give me 17.9 liter of methanol.